My name is Tudor Damien. I have my own company. We do outsourced tech support, IT consultancy, and IT advisory. So we manage right now somewhere around 15,000 servers across 9 data centers in both Windows and Linux environments and the full stack on top of them. We do pen tests and security audits. We've also recently partnered with a fellow friend of mine and his company called Availgo, and we're offering cloud migration solutions and Azure consultancy and things like that, so you can find out more about that. If you are somewhat familiar with the community in Cluj-Napoca, there's a conference that we organize there every year. It's called DefCamp. You could look into that if you're interested. My contact details, in case you want to get back to me after this session, you can find here on 2d.tel. And enough about me. This is a bit about what we do, and as I said, we're probably here that's relevant with the current topic and session. Don't worry, you will get these slides. There's more content here than we can actually cover in the time that we have, but you will get the slides from the organizers at some point. They will make them public, so don't worry, you will get all this information. If you find out you want to know more about the topic, you will get a starting point. If not, at least you've only wasted half an hour of your life, and that's it. So just to give you sort of an overview of what I'm going to talk about, I will go through a brief overview of what an IDS is, some history on the attempt to standardize the way these things work and communicate between each other and share information, because that's something that might be useful if you come to think of it. And once we go through the design consideration and figure out what the problems with these sort of solutions or devices are, we will go through some of the most common techniques to avoid them. And at the end, the part that nobody really cares about, some potential solutions and workarounds and fixes, and then lunch. So just to get things started, who here has dealt with any sort of pen testing, IDS evasion in the past? Anyone? Good, so this is new information for most of you. So when IDSs first came to be, which is around early 90s or so, people started thinking and started saying, hey, we might be better off if we had sort of a way to get all the data that these types of solutions or devices gather and have it available and shareable in between the different solutions, so that if one manufacturer or one solution detects something, this is something that could be used by other products, other similar products, to evolve as well. So the first attempt to do something like this was an old attempt by DARPA, one of the US governmental agencies, which is not a 3-letter acronym, it's a 5-letter acronym. So they wanted to develop their own interchange format. And that project is now dormant and has been dormant for a while because nobody wants to work with governments on standards. But what they did there is they defined the components of what an intrusion detection system is. And they put them into what's called the E boxes, A boxes, D boxes, and C boxes. You basically have a bunch of event generators, which could be sniffers, could be monitors. They just generate events. These go into an analysis engine, which looks at patterns, at things that are out of place, at things that shouldn't be there. And this is usually done through signature matching. Like you compare this to a known type of attack. This packet sequence that you see on the wire, you look into a large database of signatures, sort of in a similar way to antiviruses and their signatures, right? And if you find a match, then there's probably an attack occurring that's being detected by this intrusion detection system. Then you need a way to log this, to store this. That's where the logging or storage mechanism comes in. And then you might have some form of countermeasure. Could be an alarm, could be an email that's sent to somebody, could be a firewall, or could be any sort of protection that turns the IDS into an IPS. We'll see what that means in a minute. Any sort of protection that actually acts upon that detected attack and blocks it. Now, the Internet Engineering Task Force more recently started to work on a common format, which is encountered in most of the open source IDS solutions out there. So they do use that attempted standard that's out there. And if you want to know more, you can check that link out. So when it comes to intrusion detection systems, these actually stem from the physical IDSs. And you might have heard or seen some of them, right? We have a camera in the back. So even before computers, even before IDS solutions as software or as physical devices were brought to the market, you had these physical intrusion detection systems. And we're not going to talk about them, but it's just sort of to give you an idea of what's happening here. If you take this and translate this into the IT world, you get what's called a network or host intrusion detection system or intrusion prevention system. The network side of things is something that sits on the network, does some form of wiretapping, either through span ports or hub collecting. It collects all the packets in the network, and it attempts to find things that shouldn't be there, right? Find the bad guys. We're all good guys here, so we're attempting to find the other guys, right? And like you see there, you can use signature file comparisons, you can use anomaly detection, you can do stateful protocol analysis, you can do all sorts of stuff on the traffic that you capture. And this only works at a network level. So this is before that traffic hits the hosts in the network. Then you've got the other side of things, which is the host intrusion detection system, which goes beyond the basic firewall and detects changes in the system configuration, in the, if you're on Windows, in the system registry, files appearing out of nowhere, attempting to find or detect rootkits and things like that. So this goes beyond just traffic on the wire and attempts to find anomalous behavior happening on a host. And that could be different from host to host, from OS to OS. Now, if you want that IDS to go just beyond finding that stuff and logging it and possibly sending you an alert, and you want it to actually block traffic, block those attacks, this turns that IDS into an IPS, to an intrusion prevention system. That's basically the only difference. You would want an IPS instead of an IDS, because if it just sends you an alert, and it does it at 2 a.m. on Saturday morning, it might take you a while to actually do something about it. If you want to leave a device to do that for you, you need an IPS. But you might have troubles with that, and we'll see why. So these things sound like cool things to have around, right? You have this little thing sitting on your network, detecting attacks, detecting malicious traffic, and telling you about it. How cool is that? Well, it's cool up to a point, because you could run into issues based on how these things are built. So the thing is, each component of the IDS is in itself a potential vulnerability, a potential point that could be attacked and exploited. Also, you could potentially attack their availability. If you bring it down, it's down, it doesn't do anything anymore, and there's ways to do that. You could affect its accuracy. So you could generate a lot of false positives. And this is where, if you have an IPS that's blocking traffic, if it's blocking legitimate traffic, That's going to piss off your users, right? Now, when you go further and you try to affect the completeness that these devices offer, you essentially end up generating a lot of false negatives. That's traffic that's malicious, but that's allowed to pass because the device doesn't block it, doesn't detect it. And this is sort of where we are aiming to go with today's session and the knowledge that we're covering here. So there's a real need for these devices to actually give you good information, to be relevant. You don't want just another problem on your mind by using an IDS. Okay, I've put the IDS. Now, there's a lot of false positives, so a lot of the stuff that was working and it was supposed to be working is not working anymore, and it's also allowing attacks to go in. Now, did that solve my initial problem? Possibly not, right? It might just have brought in a whole bunch of other problems. So what are these problems? Well, the thing is, with IDSs, they're passive network monitors. So they're inherently fail open. What this means is, if at some point you reach the capacity, the processing capacity of that device, like 8 million packets per second or 1 gigabit per second of network bandwidth traffic going through it being processed, if you go above that, the default setting is just allow all traffic, because I can't process it. So it will not drop everything beyond that point, it will allow everything beyond that point. If you know that, you could exploit that. Now, you could, and this goes to the second point, you could essentially cause some form of denial of service on the device. Because since it has to deal with a lot of complex stuff that it has to monitor, it does require CPU, it does require memory, and it has a limited capacity as far as network bandwidth goes. So if in any way, shape, or form you can attack one of these components, and you can cause it to use a lot of memory by opening a lot of sessions that it has to track, or if you just cause a lot of traffic somehow, generate a lot of fake traffic that it has to process, it will at some point allow part of the traffic because it simply cannot process that much. Also, there's insufficient information on the wire. There's usually not enough on network packets, and even stuff that you reconstruct to form a session, there's usually not enough information to correctly reconstruct complex protocols, like SMB or RDP or any of the other RPC or any complex protocols that go beyond just sending simple TCP/IP packets. They send complex commands, and if you take those commands one after another and you end up at the 7th command in command block, and that is the attack itself, if the IDS doesn't know about that, if it doesn't recognize those complex protocols, it won't be able to block such an attack. There's also a huge diversity in how protocols are implemented, in how any sort of errors on the network are handled in the TCP/IP stack on different OSs. Some OSs just take the oldest packet that they received. If they receive 2 packets with the same ID, right, sequence ID, older OSs will just keep the oldest packet and discard the others. Newer OSs will take the newer one and replace that. And because of that different functionality in the actual implementation of the protocols, you could run into issues if the IDS handles things differently than the target host does. Now, also, usually these IDSs have trouble knowing the internal network conditions. They aren't usually aware of the network topology, of the configs on the routers, of the QoS settings on the wire, and things like that. So this is why these attacks started appearing in the first place, because people started using these solutions or devices. And I'm saying solutions or devices because they could be either software, or you could just grab a box off the shelf, and there's a bunch of manufacturers out there that have such solutions. You just plug it into your rack, you make sure that your traffic goes through that device before going into the rest of your network, and it's the device that does the job. But it essentially does the same thing as a software solution, only it's more expensive usually. So the part covering the techniques, the thing with these advanced evasion techniques is they are delivered in a highly liberal way. People doing this have a lot of time on their hands to research, to test, while the devices themselves are way more conservative. They only do their job and the job they're supposed to do, and rarely do they have some form of heuristic analysis and pattern matching and making sure that the current traffic doesn't vary too much from a baseline that they establish. And with the patterns in traffic that we see nowadays, it's really hard to detect any sort of spikes or things that are anomalous to that baseline without affecting some user who was just trying to do something legitimate. These attacks usually employ rarely used properties of certain protocols, and we'll see some of them in a minute. They use all sorts of unusual combinations. They create traffic that usually disregards protocol specifications. And it's about how the device and the OS handles this. If you get a malformed packet and you get some stuff missing or some stuff changed or some stuff that's different than what you were expecting, how do you deal with it? And this varies greatly as well. So this is another reason why these attacks happen. And these are some of the most common ones. It might not be visible to the back of the room, so I'll just go through them anyway. And like I said, you will get the slides anyway, so there's no need to really attempt to read all of them. So let's go through some of them. Insertion. This is one of the common attacks. How this works, this usually occurs when the IDS is less strict in processing the packets than the network behind it. And it ends up accepting packets that the end system just drops, rejects. So there's an example of a data stream, and you see that the sequence has to be reconstructed. So you can send packets in a random order, but you can specify the sequence inside each packet. So both the IDS and the target system have to reconstruct that out of the packets that they get. Because you might not know that, but if you send packets 1, 2, 3 in this order, they might end up 2, 3, 1 on the target. That's how networks work. So the end target has to reconstruct the data out of what it has received. So what happens here is you can see there's 2 packets with the same sequence number that were sent, and the IDS accepts the 3rd packet, the later one, which overwrites the data. So it sends all of that. It sends everything that it receives, but it just sees ATXACK. So yeah, this is not an attack. I can just allow this to pass. While the target OS actually only accepts the 1st packet and discards the 2nd one. So the data that reaches the end target is actually an attack, right? The opposite of this is called evasion. This is when the IDS is more strict at processing packets than the network. So you've got the same sequence. However, the IDS, so you send that first, you send the X first, and the IDS accepts that and discards this one, while the target discards the first and accepts the last. It's sort of the same result, but it differs in behavior on both the IDS and the target. It's very simplified. It's way more complex than this. And like I said, half an hour before lunch, not really enough to go really in depth here. The real insertion or evasion attacks are usually exploiting basic network and protocol ambiguities, either in the header fields, in the way those header options are handled, or in fragment or segment reassembly. So if the IDS and the end system differ in the ways they handle these things, you might run into insertion or evasion vulnerabilities. There's differences in protocol implementation. Because why stick to standards when you can reinvent the wheel? Now, these are some examples on where you could find these ambiguities, either in the TTL field or in the don't fragment bit set, and you send a lot of packets that are part of one large packet, and you play with the DF bit, and if that gets ignored on the IDS but gets processed on the host, it can reconstruct a large packet. And you have a lot of other stuff there as well. Session splicing, another such type of attack where the attacker splits the traffic into many packets such that no single packet triggers the IDS. So you have a longer session that includes your attack, and you split that, and you perhaps send that and time it so that, say, the IDS just thinks that the session has ended after 30 seconds, while the host thinks the session has ended after 60 seconds, so it's still waiting for packets on that session. You could just run into this because the IDS doesn't have enough memory to hold all that data. You send some of the data, then you wait for 45 seconds, the IDS says, well, this session is gone, so I'm just going to drop this and clear up some memory. You send the other packets, which is the other half of the session. The IDS still doesn't detect an attack, because that's only half the attack, so it sends that forward too, while the host was still waiting, and it receives the entire session. Does that make sense? All right. Fragmentation, that's similar to session splicing. There's actually two common fragmentation methods. One which overwrites a session, so it goes to the fragment level instead of the session level. It either overwrites a section of a previous fragment or overwrites a complete fragment. And just to be more clear, here's a couple of examples. So you have the overlap method, which sends the first packet, which is get CGI bin. The second packet is a bunch of A's and then PHXX. And then the third packet, which overwrites the XX portion of packet 2 with the data in packet 3. So you can tell it, here's a packet, just overwrite some part of the previous fragment, and reconstructing stuff on the wire works like this. You get this request. With the overwrite method, you could just send a bunch of packets and have this packet actually replace an entire packet that was sent previously. So you could just say, well, here's this, and then here's this, and then packet 3 replaces packet 2 completely, and then packet 4 replaces packet 3 completely, and what you get is this. But what you got on the wire was a bunch of garbled text that wouldn't have triggered a detection on the IDS. I did talk briefly in the beginning about denial of service. Like I said, the IDS needs to simulate the operation of all the end systems. So it has to use the resources it has to sort of reconstruct the traffic, analyze it before it's passed further along to the network. So you could trigger any sort of computationally intensive operations to cause a CPU denial of service, which is cause a bunch of fragments or segments reassemblies or any sort of encryption decryption, which takes a lot of CPU cycles. With memory denial of service, you can target any operations that use state management, like TCP three-way handshakes or TCP control blocks like SMB has. Again, with fragment or segment reassembly, you can work with that. Any sort of stuff that ends up using the memory on the device because it needs to keep all that stuff in memory to be able to reconstruct it. With network, you just overload the network. And like I said, since these devices are usually fail-open, once the network buffer is full, they will just allow everything else to go through. And you can also do a denial of service on the reactive part of these systems. You can trigger a lot of alarms. If the sysadmin suddenly gets 1,000 alarms of all sorts, even if one of them is an actual attack, he'll still say, well, that's a bunch of crap, it's just false positives, I'll just ignore all 1,000 of them because we had none yesterday, so that's clearly a false positive somewhere. So you can hide your attack inside those false positives and just cause the sysadmin to be frustrated beyond belief because there's a bunch of stuff that he just doesn't want to look at. Pattern matching weaknesses. Well, pattern matching in itself has a lot of inherent weaknesses. And if you guys are developers, you know that you don't protect your application from like SQL injection by checking for apostrophe or 1 equals 1. Because it could be the very same thing if you put apostrophe or 2 greater than 1. It's still true, but if your if clause there doesn't check but for that one case, in pattern matching, in string matching, you will miss that. So this goes without saying with IDSs as well. This request right here is the same as this request right here. If you only do pattern matching and you search for this, this will go through. You can also use Unicode evasion, and you can look into that because it's cool, for one. So if you just want to type \, you have at least 3 options to do it in Unicode. If the pattern matching system doesn't account for all of that, your request will just go through. Protocol violation. I already talked about SMB and MSRPC or SUN-RPC. In order to provide protection to such a protocol, you need to have the IDS understand that protocol. So you need to have it know about it. So you need more compute power, you need more resources to do that. And that usually doesn't happen, so you can just go ahead and attack SMB. TTL attacks, when you send a bunch of packets and you set a different TTL on them, if you know that, or you assume that the target host is behind the IDS, you just send some packets that expire at the IDS level using the TTL section. And it will get to the IDS, it will be sent further, but it will be dropped at the next stop simply because the computer says, well, that's not for me, I'm the 15th hop, so this was supposed to be dropped way back. So it ignores that packet that was actually left through by the IDS. So you can set these, and it's the same with firewalking. If you want to pass a firewall that's blocking you, you just tweak the TTL and go one step beyond that and see if something responds to your ping beyond that. Because the firewall will usually assume, hey, this guy knows what he's talking about. He knows the topology of the network behind me. He knows he wants to ping that IP, that NATed IP, so I'm just going to allow him because he gave me the proper TTL and everything. Urgency flags. There's a thing in the TCP protocol that actually tells the OS or the TCP stack to replace the last byte of the previous packet if this packet has an urgency flag. So it actually overlaps 1 byte. And you can see the result there. You send 3 packets, the second packet has an urgency pointer, and you're missing the G in the end result. If the IDS doesn't know about this, and it just sees A, B, C, D, F, G, H, I, there's something else that reaches the target. There's also polymorphic shellcode. You can actually send an attack that's encrypted using polymorphic shellcode, and you can have the code execute itself and decrypt itself once on the target to actually run the attack. So it's code that runs code that you're sending, right? And the part that gets through the IDS is the part that's encrypted, and it only gets decrypted on the target where it runs. It's sort of similar with ASCII shellcode, and this right here would execute a bin sh shell. You see the bin sh somewhere at the end there. And then you have, well, this is not really a vulnerability in itself, because encryption is cool, tunneling is cool, but you can't really do any sort of pattern matching on an encrypted traffic stream, right? So if the traffic passing through is encrypted, it's encrypted. It cannot be read. So just open up an encrypted channel and hack your servers over SSH or RDP or IPsec. So you're safe from IDSs. You could also have application hijacking. With applications that deal with media, any sort of image or streaming that's usually compressed, if there's a vulnerability in the way the application reads that data, you can create a fake BMP file. There is a known vulnerability, I think from 9 years ago, that allowed you to create some BMP files that executed code on the host where you opened the image. Now, as potential solutions, like I said, the part that nobody cares about, one thing that would be useful is called normalization, which tries to make sure that the traffic that it sees or processes is similar to what the target host would see. As you saw, most of the issues stem from the fact that the IDS processes data in a different way than the host. So the normalization process does this. It allows to sort of act as if you're the OS or the target system. And this is like the second part of the solution. You sort of have to find a way to implement different TCP/IP stacks inside these solutions or devices to have them simulate the stack on the target systems. And they have to know, well, this is a Windows system, this is a Linux system, so if this packet goes here, then I will have to process it in a different way than that packet. This is usually easier done at the host level instead of the network level. Now, there's a bunch of tools and resources that I've left here for you if you want to play around with this stuff. These tools are useful. They're actually put there with links, so if you get the slides, you just click on the links and get them and play with this stuff yourself. Those are the IDS thingies. Most of them are free. All of them are software. I did not put any sort of hardware device here. Those are really expensive. Most of these are open source. And some evasion tools as well. So there are some tools, and there's documentation out there for you to go out and try this stuff yourself, to look into this stuff yourself. So in closing, I'll just skip this. There's a bunch of courses that we do. This one should be interesting. I don't know how many of you know of Paula. There was an event earlier this year in Chicago. It had 23,000 attendees and about 1,000 speakers. She was rated #1. She talks about security. So you might want to check this out. And I'll just leave my contact info over here. I will be here for the next like 15, 20 minutes. For the guys that are really hungry, lunch is over at the main room. For the guys that have any questions, I will not keep the others waiting, and I'll wait here for you. Thank you.